ingredient that is these local clocks, sort of associating a clock cube, sort of a clock ancilla with each computational qubit. So now instead of a single global time, we'll speak of sort of a time configuration. And now the history state will be, well, unnormalized here, a sum over all the time configurations that we consider to be valid of the state of all the computational qubits at that time. And here validity means that if two qubits are supposed to go through a gate together at time t, you won't find one of them after t and one of them before t. So you have some sort of constraints on this. And so this was sort of proposed to make history state Hamiltonians more realistic for implementation. What it looks like, so you can think now, instead of a hopping particle, the Hamiltonian is really unitarily equivalent to the diffusion of a string, or in higher dimensions, some membrane. So this direction is time, this direction is space, your qubits 1 through n, and so this means, you know, that you're at a particular time, but now the construction is taking advantage of depth. And so coming from the quantum information community, they named this the space-time circuit to Hamiltonian construction. You may see the familiarity, if you're on the gravity side, to the Wheeler-DeWitt equation, right? Because we're really saying that you can take this time-independent point of view of a time-dependent process, and that you can have this history state be the ground state, h of psi equals 0, of some local Hamiltonian. So this is, you know, these are kind of, this is like your foliation of space-time, you could think of these time configurations. Okay, so that's a bunch of existing stuff about adiabatic computation. Now let's talk a bit about self-correcting memories. So this is relatively standard material as well. So classical self-correcting memories, the simplest example are ferromagnets, which we can also think of as the repetition code and the classical Ising model. So the story is that for the one-dimensional Ising model, thermal fluctuation, so imagine that you try to store a 0 state in a 1D classical ferromagnetic Ising model for a long time. Well, thermal fluctuations can flip a droplet of spins, that's inevitable. And now the energy cost of sort of growing this droplet of ones is independent of the size of the droplet, because the energy cost is proportional to the boundary, which is just constant. And so sort of there's only a constant energy barrier against excitations that, and so after some relatively short time, these excitations will permeate your memory, and your 0 will flip over to a 1. This does not happen for the two-dimensional Ising model, because in this model, the energy cost of a droplet is proportional to the boundary, which actually now scales with the size of the droplet. And so at some temperature T, droplets of size L are suppressed by this Boltzmann factor, e to the minus L over T. And this can be used to argue that the model exhibits ferromagnetic order below some critical temperature. And here ferromagnetic order means that the magnetization is going to be close, you know, it's going to be 99% up or 99% down for a long, long time. That scales sort of exponentially in the size of the overall code block, the number of spins in your Ising model. So, you know, yeah.
Sorry if this is a naive question.
No, please.
Does this also suggest to me that in the 2D Ising model, you need to constantly sort of apply energy in some sense to just maintain different memory blocks, right? So it's absolutely stable for a single bit, but what do you do with multiple bits? Do you have like special boundary locations where this doesn't apply?
So we think of the Hamiltonian as, well, it doesn't necessarily cost energy, right? This is like some physical interaction between these spins. So that's what enforces this order. So it's really a passive form of error correction.
I'm thinking about the boundary between two different bits.
Oh, yeah.
Yeah. What keeps the bits from decaying? I guess then you have to build some sort of special device where the boundaries are special.
The boundaries are special. So basically what you do is you argue that far below the critical temperature, but at some system independent size, you have a relatively, like these local excitations are relatively small and far apart with high probability. And so the probability that they ever sort of grow into each other, sorry, I'm not understanding.
No, I stated the question. I'll ask later. I stated it poorly. I'm sorry.
Oh, okay, sorry. So the idea is that this can lead to robust storage of classical information because the lifetime scales exponentially in the size of the block. This is often stated as a reason that our hard disk drives, which I guess we don't really use so much anymore, we have solid state drives, but anyway, why they would work at room temperature.
And the reason this is not inconsistent with what Charlie said yesterday is that he would call your Hamiltonian fine-tuned because there's no magnetic term.
Yeah, exactly. So because I didn't necessarily anticipate that discussion, today I'm imagining that you have an adversarial environment or, a real environment going on, but the Hamiltonian you engineer is ideal. And maybe in a laboratory that makes more sense than expecting it on a fundamental physics level. Okay, so moving to the quantum case, these memories. So quantum codes require an extra condition that classical codes do not have, which is local indistinguishability of the code words. So this means that we want topological order instead of the kind of symmetry breaking order that we just went through with the Ising model. So the archetypical example of this is the toric code. So this is a stabilizer code. So in general, you have a commuting Hamiltonian that is minus the sum of the generators of what's called the stabilizer group, or a stabilizer group. And so in the 2D toric code, which hopefully many of you are familiar with, basically you have local operators, you have plaquette operators and star operators that are your stabilizers that form this commuting Hamiltonian. And the point is that your code words are now locally indistinguishable. That's sort of the meaning of topological order, is that you have multiple ground states that can't be distinguished by local operators. And so to distinguish them or to do logical operations on the code, you have to apply very non-local operators that in the case of the 2D toric code look like long strings that sort of, so it's a torus if this has periodic boundary conditions, and these are long strings that wrap around the torus to do a logical operation. But how well does this thing actually function at non-zero temperature? Well, what you find is that these excitations occur, these pairs of abelian anions, which are really just various local Hamiltonian terms that are now upset because you're no longer satisfying them. And so these excitations occur, and what happens is these quasi-particle anions can now separate with zero energy cost. So the length of these strings can grow, and after a very short amount of time, they'll perform some logical operation and destroy your information. So sort of the quantum analog of a stable, of the 2D Ising model is the 4D toric code. And in this model, the logical operators are two-dimensional membranes, sort of everything is doubled in dimension. And then the energy cost scales as the 1D boundary of those membranes. So the errors are now suppressed by this exponentially small Boltzmann factor because you get macroscopic divided by some constant temperature. This argument about the energy barriers is not really, I would say it's almost not necessary or sufficient. It's more of a intuitive argument that people have used in the past to justify these self-correcting models. Okay. And then it's an open question whether you can have a quantum system, a local Hamiltonian, with finite temperature topological order in 3 dimensions or less. And I won't address this question today. So when I make use of topological quantum memories, I'm thinking of living in a higher dimensional space-time, I'm kind of taking advantage of the freedom that we give ourselves in Hamiltonian complexity, where we can describe a k-local Hamiltonian just in terms of its combinatorial locality without worrying too much about spatial locality. But these things are spatially local in some high number of dimensions. So now I want to tell you about not the 4D toric code, but something a little more involved. So these are self-correcting memories with universal local operations. So by only doing local operations on them, you can achieve a universal quantum computation. So this was studied by Bombin et al. And so an example is something called the 6-dimensional color code. And here it's not only self-correcting as we saw with the toric code, but it also allows for transversal gates, a large set of transversal gates here, but you don't get a transversal Hadamard gate. So transversal just means that you have a local Hamiltonian that generates a constant depth unitary to perform the gate. And So you use a trick called gate teleportation. So there's no quantum error correcting code that has a universal set of transversal gates, but you can use a gate teleportation trick to get the sort of last gate that you need to make this set universal. So this gate teleportation really just depends on being able to prepare logical states, x and z, measure these logical x and z operators, and apply logical x and z condition on measurement outcomes. And this is where you use sort of measurement and classical post-processing in the standard view of fault tolerance. So again, this existing work is in the standard time-dependent view. And you could think of when you apply gates, it creates a brief interruption to metastable equilibrium, because unless you apply all the gates simultaneously, the code will perceive that as an error. So you're very briefly in a high energy state. They propose various solutions like turning off the stabilizers while you apply the gates, or maybe it's not a problem that you're briefly in a high energy state. And this is a proof of principle scheme. Obviously nobody's going to build this. That resilience to thermal noise is possible. So now I'll tell you a bit about our construction that combines these ingredients. So the logical qubits in the original computation are going to each be made of physical qubits so m here is the number of physical qubits per logical qubit, which we should think of as macroscopic. And each physical qubit has its own clock qubit. So both the computation and the code stabilizers are enforced by local Hamiltonian terms. So we're going to have a part of the Hamiltonian that enforces sort of the propagation of the clocks with the local gates, and we're also going to have another part of the Hamiltonian that creates these interactions, these code interactions between the particles, right? So if you like, so when we rotated away to another frame and got rid of everything on the computational register in the original construction, this is like the physics of a free theory. There's no interaction between the quantum bits on the computational register. Whereas I'm sort of saying the missing piece here is that you can include interactions in between the qubits on the computational register, and these sort of enforce that you're in some code space. So I've written these as sums over time configurations, and these are going to be sort of time dependent in a complicated way, but are going to remain local. And here time is just sort of this, everything is time independent, time is just a parameter. So the propagation Hamiltonian needs to consist of local gates, and the code Hamiltonian also needs to sort of accommodate the propagation of the circuit without there being any frustration, because this would lead to something like Anderson localization along the time direction. So really the scheme I described could apply to any fault tolerant scheme with local code checks and local operations to get your universal gate set. It's not restricted to the code model being self-correcting. That's just if you want this full thermally stable property. And actually for practical usage in quantum annealing and adiabatic computation, I'm also interested in applying this to smaller codes, but I won't go into that. And okay, so this part about gate teleportation using logical measurement and classical post-processing, that all has to be part of the history state. And so the Easton-Knill theorem that says that there's no universal set of transversal gates is really the thing that's forcing us to include classical post-processing in the history state itself. And that classical post-processing is of polynomial depth, but that's all going to be okay. So transversal unitaries in a local Hamiltonian, as I described, so if you had a single unitary gate acting on a logical qubit, so you're just trying to do a single qubit logical gate, this should sort of decompose as a tensor product of local unitaries acting on the physical qubits. That's what it means to be a transversal operation. So advancing all of the clocks in a given logical qubit at once would not be a local operation, right? It wouldn't be a local Hamiltonian term. So we need to be able to advance the local clocks independently from one another by these sort of local terms. So we just have some sum of local propagation terms over all the qubits in a given code block. And we also want to protect these clocks from getting too far out of sync from one another. So this propagation term kind of checks your neighboring clocks before moving on to advance it. So you could think of this as a membrane in some higher dimension, and this thing I'm talking about here sort of enforces the continuity of this membrane as it dynamically evolves. So now, this was an interesting challenge. So if you advance the clocks one at a time, this would violate terms in the code Hamiltonian. And so to solve this, we have to describe a form of sort of dress stabilizers. So what those look like is that now your stabilizers of your quantum code check what time it is so that they can be adjusted to accommodate this propagation. So basically, the stabilizers might act on, so imagine you have a stabilizer of the toric code, but now not all of the qubits are at the exact same time. One of them might be at t-1, one of them at t+1, and one of them at t. Well, what you do, and what this expression is saying, is just that you rotate the ones that are ahead to go backwards, the ones that are behind to go forwards, so you sort of catch everybody up so that you can apply your stabilizer term. So it's not really so deep, but I think it's interesting. It's kind of like a space-time view of the advanced or retarded potential in electromagnetism. Does
that work with just sort of like nearest neighbors, or do you need to have some hierarchical structure to get it to grow?
So the local terms are, I mean, the stabilizers are local themselves, so you have to include an additional number of terms equal to the number of sort of rotated checks you're willing to do, right? So this scales exponentially in the size of the stabilizer, but that's constant.